warp speed is one of science fiction's most seductive concepts, made famous by the iconic TV show Star Trek. It solves the biggest problem humanity has with space exploration: distance. The closest stars are light years away, and using conventional travel methods that achieve only a fraction of light's speed would take decades or even centuries to reach them. This is why the concept of bending space, warping space-time, and surfing across the galaxy in a warp bubble has always captured the fascination of dreamers, writers, and scientists alike. But is warp speed even possible, and does it break the laws of physics in trying to achieve it? At the heart of the debate is Einstein's theory of relativity. According to special relativity, no object with mass can reach or exceed the speed of light. The faster something moves, the more energy it takes to accelerate it. And as it approaches light speed, that energy requirement becomes infinite. This isn't just a technological challenge, it's an unbreakable law that is built into the fabric of the universe. That alone should shut the door on faster than light travel. Or does it? In 1994, physicist Miguel Alcubierre developed a radical solution within the framework of general relativity. What if you didn't move through space at all? Instead, you bend space itself, contracting it in front of your ship and expanding it behind. The spacecraft would ride inside a warp bubble, surfing a wave of curved space-time. Within the bubble, the ship wouldn't technically move faster than light in its local frame, preserving Einstein's cosmic speed limit. Outside the bubble, the ship would appear to observers to be moving faster than the speed of light. A cheat code, built right into the geometry of space-time. At first glance, it sounds perfect. No physical laws of the universe are broken, just space being bent and manipulated. But the math behind the Alcubierre drive isn't so forgiving. The original model required exotic matter, something that has negative mass or negative energy density, to create and maintain the warp bubble. This kind of matter has never been observed in nature. It's not just rare, it might not exist at all. Some physicists argue that even if negative energy is theoretically possible, the amounts needed would be astronomical. Initial calculations suggest energy requirements would be near infinite to bend and maintain a warp bubble. It violates the fundamental energy rules of relativity, making warp travel not just unlikely but outright impossible according to the known laws of physics. Even though the idea of a warp drive may exist mathematically, it requires a type of energy that isn't even possible in our real universe, so the concept of warp speed is nonsensical. Or is it? Over the years, theoretical refinements have chipped away at the energy problem. New models suggest that under the right conditions, the amount of exotic matter needed could be reduced to the energy equivalent to the mass of our Sun, or even as little as a planet the size of Jupiter. An ungodly amount of energy just the same. Imagine turning the entire mass of Jupiter into energy just to bend space to create a warp bubble. In 2021, physicist Erik Lentz proposed a new kind of warp drive that wouldn't need exotic matter at all. Instead, it would use something called a soliton, a stable, self-contained wave of energy moving through space-time. In theory, this wave could carry a spacecraft faster than light, all while staying within the known rules of Einstein's equations. But like Alcubierre's proposal, Lentz's solution still relies on enormous, perhaps unreachable amounts of energy, and remains deep in the realm of speculation. This is where the controversy of a warp drive ignites. On one side are the physicists who see warp drives as nothing more than mathematical curiosities, solutions to equations that look intriguing but collapse under scrutiny. They argue that physics is filled with speculative solutions, that don't reflect any semblance of reality. Just because something fits into general relativity doesn't mean it can exist in nature. These critics also point out that we still lack a quantum theory of gravity, which would likely impose additional constraints on space-time manipulation. They argue that warp speed is just science fiction dressed up in relativistic clothing, but others see those who refuse to accept the possibility of warp speed travel as a failure of imagination. They argue that history is filled with seemingly impossible ideas that later became reality. From air flight to space travel to nuclear power, every major leap in science once stood on the ground that others thought was unwalkable. They point to Casimir effects and quantum field anomalies that hint at the existence of negative energy in tightly confined spaces. They suggest that advanced civilizations, with technologies millions of years ahead of ours, might have figured out ways to stabilize and exploit these phenomena. From this view, warp speed doesn't violate the laws of physics. It operates in the domain of those laws we don't yet understand. Then, there's the gray area, where most serious physicists find themselves. They don't dismiss warp drives outright, but they don't buy the hype either. They acknowledge that general relativity allows these solutions on paper, but caution that practical implementation is another story. The universe always unequivocally enforces its laws, even when our equations hint at a workaround. The deeper laws of physics, such as energy limits, cause and effect, and quantum unpredictability, unravel the dream of a functional warp drive, pulling it back into the realm of impossibility. But supporters of the warp drive concept remain optimistic, because if even a sliver of warp theory proves real, it could redefine humanity's future and our place among the stars. Regardless, many more roadblocks remain. Causality presents one of the most complex problems. Faster than light travel, even if it's achieved through warping spacetime, would potentially lead to paradoxes. Scenarios where things happen before their causes, or messages that are sent into the past, create contradictions that challenge our understanding of time, causality, and the very structure of reality. It's one of the strongest arguments against faster-than-light travel, including when it's achieved by a warp drive. It would lead to causality violations so extreme that the universe itself would forbid it. But general relativity does allow for certain extreme space-time shapes, or warp geometries, that could create closed loops in time, opening the door to certain paradoxes. If time loops and causality violations are possible, they could lead to classic paradoxes, like arriving in the past before the event that sent you there. Most physicists see this as a red flag, a sign that any faster-than-light solution may most likely be impossible. But others suggest that quantum mechanics or unseen factors that might secretly guide quantum events could resolve these paradoxes in ways we don't yet understand. Then, there's the energy discharge problem. Some models suggest that when a warp bubble is collapsed, it would unleash massive amounts of energy and vaporize anything close to the destination zone. Think gamma-ray bursts or intense waves of concentrated radiation. In this view, warp travel isn't just hard, it's dangerous, even lethal. A single miscalculation could mean annihilating everything in the path of the bubble. It's the ultimate cosmic wrecking ball wrapped in Einstein's equations. The fact that warp drives even exist as legitimate topics in peer-reviewed physics is remarkable in itself. 50 years ago, the very idea would have been laughed out of the room. Now, it lives in the margins, half fiction and half on the edge of the frontiers of science. The question of whether warp speed breaks the laws of physics doesn't have a simple and clear answer. As of now, according to our best understanding of relativity and quantum theory, warp drives are mathematically interesting, but physically unverified and exist only in the realm of theoretical. Some say impossible, others say improbable, but there are a few who say inevitable. I'd like to thank you for investigating the possibility of warp speed and whether it breaks the laws of physics. And I invite you back for our next episode,